Welcome back. So in this week we are going to discuss about process management and CPU scheduling. That what is a process, what is a thread, how the process life cycle goes on, what are the different algorithms for the process scheduling by the CPU and so on. So let's get started. First of all, we start with the process. A process is a program in while executing. So when a process is in execution state, we call it as a process. A process has all of its own dedicated resources, code section, text section, global and static variable section. Memory is allocated during the runtime that is also assigned to a process. It has its own stack to hold the temporary data, and it has all the associated resources with it, like which are the open files, which are the network connections, everything. Just for example, if you open a Word document, so when the Word document is a is executing, it becomes a process. Till it is in passive state, it is not executing, it is a program. But as soon as it comes in active state, when it is executed by the processor, it becomes a process. Now it has its own memory, its own file handle, own window, everything. Thread. A thread is known as a lightweight process. It is a lightweight unit of execution within a process. So, a process, each process has at least one thread, like for the main thread, which is called as the main thread. A process, each process has at least one thread, which is the main thread. Now, a process can have multiple threads, and each thread will share the same resources as the process. But each thread has some of its own independent units also, like it has its own ID, its program counter, register set, stacks, everything. These are different. For example, a web browser like Chrome, the browser itself is a process, but that process has multiple threads. One thread may be to handle the user interface, another thread to perform some to execute some scripting codes, another thread to show the error messages, another thread to download a file, and so on. So overall process is comprised of number of threads. But again remember, there must be at least one thread. If you see here, a process consists of multiple threads. If there is only single thread, if there is only a single thread, then code, data, files all are shared and registers and stacks. But when we are having a multi-threaded process, that means we are having multiple threads within the same process, then code, data, and files will be shared among all the threads, but each thread will have its own registers and stack. Each thread will have its own registers and stack. So, what is the difference between a thread and a process? Whenever, the first difference, let's talk in terms of resource allocation. Whenever we run a program, so it becomes a process. So, new resources are allocated each time to a process. But while we create a thread, no new resources are allocated since thread shares the resources of the process. Another one is resource sharing. Resource sharing, the code may be shared for some programs, but generally resources are not shared between different processes. But threads share the code, heap, data, area, everything except the stack. Each process has its own separate address space, but each thread has the same address space which is given by the process. The processes communicate through the IPC, that is the inter-process communication, whereas Threads communicate by sharing the variables, like we say message passing, or by sharing the variables because they have a common address space. Context switching, in terms of processes, context switching is a slower than threads, but in case of threads, the context switching is faster. Why it is so and what is the context switching? We will just talk about it. So, okay, let's see a analogy, restaurant analogy, that what is a process, what is a thread, how it works. Let's say the restaurant, which is my CPU, has one kitchen. That is the core of the CPU. It may have multiple kitchens, that means it may have multiple cores, but let's talk about only one core, one CPU core. There are multiple chefs. So each chef is a process. One chef for Italian, one chef for Mexican food, and so on. So each chef will have their own private workspace, which is called as the memory space. Each will have their own recipes, which is their code, and each will have their own ingredients, which is the data. So they do not share ingredients easily. If they if they will share, that will share by IPC, that is the inter-process communication. Now, each chef may have some line cooks with him. Like Chef Italian has three line cooks, threads T1, T2, T3. They all work together in the same kitchen space, sharing the same ingredients and recipes to make the pizza quickly. So, creating a new chef, like hiring a new chef with his own specialization, own resources, own private workspace, is difficult. It is a slow process. But if you want to have a line cook, that is an easy process. So creating a thread is easier and it's a lightweight process than comparing to creating a process because it requires every resources. Now, let's talk about the life cycle of a process. So the life cycle of a process consists of 5 states. These are the new, ready, running, waiting, or also called blocked, and terminated. As soon as a new process is created, it is in the new state. For example, you double click on application icon like Word or Notepad or something to open it. So as soon as you click on it, it becomes a new process. Now, once you click, the process is loaded in the memory and wait for its turn by the CPU for its execution. So the process has all the required resources which it requires for the execution, but it is just waiting for the processor for its execution. So it is called as the ready state. When you are having all the resources for execution, but you are waiting for your turn. You are waiting for your turn. There. So it is called as the ready state. Then running state. Now CPU is executing your process. CPU is executing your process. Make sure one core at a time can execute one process. So CPU is executing your process as soon as your turns come. So that is called as running state. Now, suppose while running the state, process requires some external input, like it may require some user input for execution, or it may require some file, it may need to read data from some file or something. For example, you are writing a code to add two numbers input by user. So when the program is running, it will wait for you to input two numbers. So it is dependent on the external factors. When you will enter the input, then it will execute further. So till it waits for the external input to complete, that is called as waiting state or blocked state, because process cannot continue until that event is fulfilled, until that event occurs. The process cannot continue. So we call that as waiting state or blocked state. Now, once the process has completed its execution, or we are forcibly closing the process, right? Then it is called as The process is terminated. When the process is terminated, all the resources acquired, all the resources acquired by the process are released. So this is the flow chart for the process states, the life cycle of a process. So if you see, a new process is created. Once it gets all the resources, it enters into the ready queue. Now, from the ready queue, when the processor is free, when the CPU gets free or this process gets its turn, it is dispatched to the running queue. If it's times out or if it's times out, for example, in round robin scheduling, we will talk about it. So it comes back to the ready state. Or if it wait for a external event like user input output or file reading, something like that, then it comes to the blocked state or waiting state. Once that event occurs, it goes back to the ready state. So this cycle goes on. And when the process completes, it goes to the terminated state or exit state and it releases all of its resources. So, what triggers the transitions? How the transition from one state to another state happens? From new state to ready state. When operating system has finished loading the process into memory, the process is in memory, it acquires all its required resources, then it comes from new to the ready state. Then from ready to running state, the operating system scheduler selects this process to run next. This is called as dispatch, as we saw it here. Then from running to ready state, the process has used up its allocated CPU time slice or a higher priority process becomes ready. Now, for example, the processor is given a 2 microsecond time to each process. Whatever the length of the process is, if it is giving a time of 2 microseconds. So in that case, it will execute for 2 microseconds and then the process will go again back to the ready state. We will talk about this later on, just now in round robin scheduling and what is the preemption also. From running to waiting state, the process requests something it must wait for, like an input output operation or input request. Like we said, it is waiting for you, user, to input two numbers. So it is waiting for something. So it comes into the from running state, it comes to the waiting state. When the event of the process occurs, like input output completes, it comes back to the from waiting state to the ready state. And when the process finishes all of its work or you forcibly kill the process, it comes from the running state to the terminated state. So these are all the transitions of a process life cycle. A real world example, like you double click the notepad icon. So it is the new state. Operating system loads the notepad program in the RAM. So it now waits behind other apps for the CPU. It becomes the ready state. Now the scheduler gives it the CPU. So the window opens up and ready for input. Then it is the running state. Now you click in the file menu, you click the open option. So Notepad now waits for you to select a file until you select a file. So that is the waiting because Notepad is waiting for you to select a file. So that is the waiting state. Now you have selected a file, the file is opened, the input output operation is complete, that means. So Notepad is ready again to run. So it is in the ready queue and waiting for the CPU. So as soon as the CPU is free, so the Notepad runs again to load the file contents into the window. So again it is the running state. Now you type nothing. So it is again waiting for you. Either you select some option from the menu bar or you type anything, delete anything, you perform some operation. So it is waiting for you. So that is the waiting state. You click X or to close the window. or you save your file and then close the editor. So that is the terminated state. So this is the cycle. This happens basically same for all of the applications. So this is how the process life cycle works. If we compare the processes and thread, a process is a heavyweight process, isolated unit of resources, because it has all process has their own resources which they do not share. Whereas a thread is a lightweight process, it's an efficient unit of execution within a process. And since a thread is a part of a process, so they share all the resources given by the process. For efficiency and performance within a single application, we use threads. A process life cycle is always from one of these five states. It is the operating system scheduler who manages the transition, like from when the process from the ready state will go to the waiting state, from running state to ready state to running states, and so on. Now, we use the term context switching. So, what is this? Suppose one process is executing by the processor, then next process comes in for execution. So CPU will leave the first process and start executing the next process. So CPU requires to so saving the old process in memory, saving the state of old process and loading the state of new process is called as the context switching. Context switching is the process of saving the state of a currently executing process and loading the saved state of the next one to run. When we talk about multitasking operating system or multi-processing or multi-core operating systems, multi-core systems, there are multiple processes which resides in the memory of the operating system, right? Now, one process is executing. So what happens basically? Suppose we are having a single core, we are having a single processor, but it feels like we are multiple applications are running simultaneously. Like you are printing something, like your printer is printing the output on a paper which is attached to your computer. On one side, you are typing something in your Word document, and simultaneously, you are listening to the songs also on a media player. Okay, so multiple applications are running parallelly. How it happens? Whether we, while we are having a single processor. So how it happens? What your processor does, what the CPU does, it allocates a time unit for each process. Like for suppose 2 milliseconds. Each process will be executed 2 milliseconds because a processor can execute one process at a time only. So, and so what processor does, what CPU does, it switches between the processes for every 2 milliseconds. Like for 2 milliseconds, it will play the song. Then for 2 milliseconds, it will take a printout. Then for 2 milliseconds, it will perform the operations in your Word document. Then again for 2 milliseconds, it will play your song and so on. And this switching is so fast that we think that all the operations are executing simultaneously. So when a song is playing by the processor, after 2 milliseconds, it will go to print the document. So processor needs to save the context of this media player, that up to which point it has played the song. And then it needs to load the state of the printer, that up to what point it has printed. So it needs to switch between two processes. That is called as context switching. So to have a illusion that multiple processes are executing simultaneously, we require context switching. Or to efficiently use the resources, we require context switching. So context switching are caused by scheduler decisions like a process time quantum expires. As I said, for example, we are having a time quantum of 2 milliseconds. So each process will execute for 2 milliseconds. Or due to the interrupts, like a high priority process comes in. So CPU will leave the old low priority process and will load the high priority process. So again, there is a context switching. User request, a process voluntarily yields the CPU. Like for example, input, output, and so on. Like a chef, which is my CPU, quickly switching between recipes. A chef is preparing multiple recipes at the same time. So he will switch between the both of the recipes simultaneously. It is not like that he is preparing both recipes at the same time. What? He will switch. First he will do something in one recipe, then in other recipe, then in first recipe, then in the second recipe. So that is the switching. And he must remember that what he has done in the first recipe and now what he has to do in the second recipe. So that is called as context switching. Now, when we save the state of a process, as we said, while doing the context switching, we need to save the state of a process. So the state of a process is saved in the PCB, that is called as process control block. It is a data structure which is used to hold the state of a process. So it is the basically its IDs. So what is a PCB? It holds its state, that what is it is running, waiting, ready, what is the process state at this time, what is the process ID by which we uniquely identify the process, what is the program counter, that which instruction is next to be executed, which registers it is using like accumulators, index registers, etc. CPU schedule algor information like what is the priority of the process, what are the pointers towards the queues, memory management information, accounting information, input output status information, all this information, everything related with the process is stored in the PCB for the context switching, so that CPU, whenever CPU has to load the process again, it reads the information from the PCB and loads accordingly. Like PCB, it has all this information like process pointer, process state, process number, process counter, registers, memory limit, list of open files, and so many other things. So, what are the steps of a context switch? When operating system decides to switch from process A to process B, we are having two process A and process B. Operating system wants to switch from process A to process B. The current flow is interrupted. So, the first of all, the current flow, the process A is executing currently. So, current flow is interrupted, that you need to stop it. So, when you need to stop it, first of all, you will save the state of process A into its PCB. And then, using the operating system scheduler, you will choose process B to run next. So, when you are going to choose the next process to execute, the PCB for process A is moved to the appropriate queue because PCB process A is executing right now, but it is stopped. So it will go to the ready queue or input output queue, and process B is marked now running because now process B is running. So you need to load the PCB of process B so that CPU will know that up to what state it has been executed, what is the status of process B. You need to flush the TLB. TLB is the translation local site buffer. It is basically a cache memory. So to avoid the security breaches, we use the TLB. We flush it every time, and then CPU begins executing the process B. So whenever we need to, in simple steps, whenever we need to perform the context switching, whatever process was executing, we will stop it, save its state in the PCB, then the other process which we want to execute, we will load that again. We will read its PCB, load the process and execute it. And accordingly, we will need to change the states of the processes. Now, this whole process is totally a overhead, right? Because the more context switchings you will do, the more overhead for the CPU will be. So we always try to minimize number of context switches. We cannot purely eliminate context switches, but we try to reduce the numbers, because whenever context switching is being done, that means processor is not executing any user process. It is not doing work for the user, it is doing internal task. So which is a purely overhead wastage of CPU. So the cost of context switching, direct CPU time. As I said, in load saving the PCB, in reloading the PCB, all the operations we are using the CPU, which is a CPU loss. Cache memory issues, we need to update the cache always. So that is TLB flush. So always excessive context switch can severely degrade system performance. This is why choosing the right quantum in round robin is critical. We will talk about this now. So let's talk about CPU scheduling algorithms. That we said that operating system scheduler decide the process which process will be executed by the CPU. Now how this decision takes place? There are several scheduling algorithms like first come first serve, to which we call as FCFS, shortest job first, SJF, priority algorithm, round robin. One more we are having is SRTF, shortest remaining time first. CPU scheduler. It is a module of operating system which selects that which is the next process which will be executed by the CPU. Again, there are multiple processes which resides in the main memory at the same time. It is the task of CPU scheduler who decides that which process will be executed by CPU. Ready queue is the queue where all the processes who are waiting for the CPU are stored. A process is in ready state, that means it is just waiting for its turn by the CPU. So all these processes resides in the ready queue. Burst time. Burst time is the time it is the time a process needs. It is the time a process needs before it must wait. It is basically, you can say, the execution time of a process, that how much time it requires for its execution. And the context switching, as we have discussed, the process of saving the state of one process and loading the state of another process. So what happens when a process is running and a new, more important process enters the ready queue? Does the current process gets to finish, or it kicked off, or is it kicked off? Right. So we are having the scheduling algorithms of two types. One we call as non-primitive scheduling, which we call as the polite approach, and one is the primitive scheduling, which we call as the bossy approach. Now, let's discuss about what we mean by the non-primitive scheduling. A non-primitive scheduling is if a process is running, executing by the processor. Let's say the process P1. CPU is executing this process. This process cannot be released by the processor until it completes it, until it finishes its execution. So that is called as non-primitive scheduling. If a process is being executed by a processor, the processor cannot leave the process in between until the process is until the execution of process is complete. So a scheduling discipline is non-primitive. If once the CPU has been allocated to a process, the process keeps the CPU until it releases it. So how it can release the CPU? It terminates or it voluntarily switches to the waiting state. For example, if you borrow a book from a library, no one can take it from you until you finish reading it and return it to the library. So that is the non-primitive. So the pros of this, the simple low scheduling overhead, but cons of this are it can lead to poor response time for interactive systems if a long process is running. For example, this process P1 is very long. So it will keep the processor with itself for a long time, which will lower the response time. On the other hand, primitive scheduling. Our scheduling is primitive if a process can be forcibly taken from the CPU. It is executing and you can you can take it from the CPU. Then it becomes a primitive scheduling. A scheduling discipline is primitive if the CPU can be forcibly taken away from a running process before it has finished its CPU burst. Like process has not completed, but you are taking the CPU from the process. When it can happen? Like when a new process arrives with the shorter burst time, like shortest job first. We'll talk about it. When an interrupt occurs, like a timer interrupt from the clock or a process, we can say, or also we can say the priority queue based on the priority, or when a process moves from a waiting to a ready state, like the input output completion. So these are the some of the scenarios where this preemption can happen. You're watching TV and someone else comes in and take the remote and change the channel. So you were watching something and someone else comes, takes the remote and changes the channel. So that is the primitive because the processor has been taken from you. The benefit of the primitive scheduling is it allows for better response time and is essential for interactive and multi-user systems. But on the other hand, the drawbacks are it requires careful handling of shared data, high overhead due to the context switching, and it is really complex to implement. So, if we classify the algorithms, that which algorithms are which? First come first serve is a non-primitive algorithm. Shortest job first is again non-primitive algorithm, but shortest job first can be implemented in terms of primitive also, which is called as shortest remaining time first. This is the primitive version of SJF. Round robin and priority scheduling, all these are primitive algorithms. So, in case of primitive schedulings like SRTF or RR, shortest remaining time first and round robin, benefits are better performance matrices like average waiting time, response time, but drawbacks are higher overhead due to the frequent context switches. On the other hand, in case of non-primitive schedulings, lower overhead, fewer context switches, but the problems are of worse performance for interactive systems. The choice depends on the system's purpose, that what you can um, negotiate with actually. So, how we determine that which scheduling algorithm is good? Basically, there are some matrices which we use for, there are some scheduling matrices which we use to identify that which scheduling algorithm is good, which one we should use. The first is CPU utilization. Our ultimate purpose, what we want to keep CPU as busy as possible. So the algorithms which keep CPU at most busy, that is the one matrix that which algorithm is keeping the CPU more busy. The idle time of CPU should be as least as possible. Another is throughput. Number of processes completed per unit of time. Like within 1 second, how many processes are completed. That is called as the throughput. So the throughput should be as high as possible. That is, there should be more processes completed per unit of time. Waiting time. Total time a process is spent waiting in the ready queue. It should be as minimum as possible. If a process is in the ready queue, it should get the chance as early as possible. The waiting time should be as minimum. Turnaround time. A process enters in a ready queue or a ready state and then process completes. The total time, that is called as the turnaround time. Like the total time for the process completion, including all the input output waiting time and everything. So it is calculated by finish time minus arrival time. Response time. Time from submission until the first response is produced. Like as soon as your process reproduce the first response, that is called as the response time. Basically, we focus on two key matrices, that is the waiting time and turnaround time. Our focus is always to minimize waiting time and turnaround time. Now, let's start with first come, first serve. As its name says, first come, first serve. The process who enters the ready queue first will get the CPU first. That will be served first. So, it is the simplest scheduling algorithms. Processes are assigned to the CPU in the order they requested. So, a simple ready queue is required. It is easy to implement, easy to understand, but the problem is of Conway effect. For example, a very in the queue, first process is a very long process. So, if it is a long process, and for example, after this, we are having very short processes. So, these two processes has to wait a long because they are waiting for a long process to complete. So, this process has to wait a too much. So, it is called as Conway effect. When short processes needs to wait a lot due to the completion of a long process, it is stuck behind, right? So this is called as Conway effect. So FCFS has the problem of Conway effect. Now, for example, we are having three processes P1, P2, P3. All these three processes arrive at time 0. That means all these three processes reach in the ready queue at the same time. Burst time, that is the time required for these processes to complete. P1 requires 24 milliseconds, P2 requires 3 milliseconds, and P3 requires 3 milliseconds. These are their burst times. So, if we draw their Gantt chart, process P1 enters first. For example, let's say P1 is the first process, then P2, then P3. They arrive at the same time in the ready queue, but the sequence is this one. So, first of all, P1 will be executed. So, it will execute after 24 seconds, 24 milliseconds. Then P2 will execute. So, it will start at 24 and the burst time is 3 milliseconds. So, it will complete at 27 milliseconds. Then process P3 will start. It will start at 27 and the burst time is 3 milliseconds. So, the total time will be 30 milliseconds, right? So, this is the Gantt chart. Now, if we calculate the waiting time for all the processes, because we said that our main focus is on waiting time and turnaround time. Okay, for how long process P1 has waited here. Let's talk about waiting time. Process P1, the waiting time of process P1 is 0 because it starts at point 0. There is no waiting time for P1, so the waiting time for P1 is 0. Waiting time for P2 is 24 because after 24 millisecond the turn of P2 comes. So the waiting time for P2 is 24 and the waiting time for P3 is 27. So what is the average waiting time? 0 plus 24 plus 27 divided by 3, and it comes out to be 0 plus 24 plus 27 divided by 3, that is the 17 milliseconds. So 17 milliseconds is the average waiting time. Now if we talk about the turnaround time when a process enters and when it completes. So that is the finish time minus the arrival time. Process P1, the turnaround time for process P1 is 24 because it is completing at 24 milliseconds. The turnaround time for process P2 is 27 because it completes at 27 seconds, and turnaround time for process P3 is 30 because it completes at 30 milliseconds. So average turnaround time will be 24 plus 27 plus 30 divided by 3. 24 plus 27 plus 30 divided by 3, which is 27 milliseconds. So average waiting time comes over here as 17 millisecond and average turnaround time is 27 millisecond. Now you can see the problem here that P2 and P3 are the smaller processes, but they have to wait a long due to the long process. Then next comes out to be the shortest job first. In shortest job first, we check which process has the shortest CPU burst. The minimum the CPU burst, that process will be executed first. So our main purpose is execute the process with short CPU burst. So the smaller processes will be executed first, longer processes will be executed later on. It can be non-primitive, and once the CPU is given, it cannot be primitive until completes its burst. Or it can be primitive, which is called as the shortest remaining time first. If a new process arrives with a shorter burst, it preempts the current process and load the new one with a shorter burst. SGF, shortest job first, is one of the most optimal algorithm in minimizing average waiting time, but the problem it can have of starvation. Starvation, let's say we are having some process P1, P2, P3. P1 is having a shorter burst, like 5 second, it is 10 millisecond, it is 15 millisecond. A process of 5 millisecond is executing. It is executing. In the meanwhile, one more process P4 is loaded with burst time of 4 millisecond. The 4 millisecond is executing. In the meantime, one more process is loaded with a burst time of, let's say, 5 millisecond, and so on. So what will happen? The process with the long burst time will have to wait a lot. They will starve for the CPU because the processes with the shorter burst are coming and CPU is given to them. So the processes with the long burst time, they have to wait a long. So they will starve for the CPU. So the problem, and it may happen that certain processes will not get their turn ever. So this is called as starvation. And the solution of starvation is the aging. Solution of starvation is the aging. The concept of aging is if a process is waiting for the long time in the queue, then you increase its priority. Basically, you move it further in the queue for execution. It is impossible basically to know the length of the next CPU burst cycle, so you just need to predict here, so it becomes little bit tricky. Now let's, for example, let's see a numerical here. We are having okay, let's say we are having four processes now, P1, P2, P3, P4. They all arrive at the same time. Their burst time is 6873. Now, unlike FCFS, first of all, we will see the process with the smallest burst time. P4 has the smallest burst time. So P4 will be executed first from 0 to 3. Then P4 is executed now from the rest of the processes. P1 is having the smallest burst time. So P1 will be executed from 3 to 9. The total time is 6 milliseconds. Then P3 will be executed, which is the 7 milliseconds, and then P2 will be executed, which is the 8 milliseconds. Right? Now, if you calculate the waiting time of each process, what is the waiting time here for process P1? P1 has to wait for 3 milliseconds. What is the waiting time for process P2? P2 needs to wait for 16 milliseconds. The waiting time for P3 is 9 milliseconds and the waiting time for process P4 is 0 millisecond. So the average waiting time is 3 plus 16 plus 9 plus 0 divided by 4. 3 plus 9 plus 16 plus 0 divided by 4. So which is the 7 milliseconds. So average waiting time is 7 milliseconds. If we check the turnaround time for P1, the turnaround time for P1 is 9. The turnaround time for P2 is 24. The turnaround time for P3 is 16 and the turnaround time for P4 is 3. So average turnaround time is 9 plus 24 plus 16 plus 3 divided by 4, which comes out to be, which is, you can calculate it. So this is your average turnaround time. The next one is priority scheduling. Priority scheduling is with each process, we assign a priority number. With each process, we assign a priority number. Generally, lower the number means higher the priority. Like if the number is 1, that means the highest priority, and number 10 is means the lowest priority. Generally, sometimes higher the number, higher the priority, but most of the time lower the number, higher the priority. So with each process, we assign a priority. Now, the process with higher priority will execute first, the CPU will be given to them, and the process with the lower priority are kept behind. Again, it can be primitive and non-primitive. If once a process is given to the CPU, until the process completes, it cannot be uh, CPU cannot be taken off, then it comes the non-primitive. But if a process is executing and a higher priority process comes in, so we stop the current process and we load the new higher priority process. Then in that case it becomes a primitive scheduling. Again, the problem of starvation is there. It may happen that low priority process may never execute because a higher priority process are coming and coming and coming in the queue, and lower priority process will not get their chance. So what is the solution? The solution is aging. In case of aging, if a process has waited for a long time, then we increase its priority gradually. So at one time, a lower priority process will become a higher priority process and it will get the CPU for the execution. For example, let's discuss one example. Let's say we are having four processes again. Lower number means higher priority. Their burst time is 4, 3, 6, 5 and the priorities are 3, 1, 4, 2. Now, let's see which process has the highest priority. Process P2 has highest priority. So if I draw the Gantt chart there, the P2 will execute first from 0 to 3 because it is burst time is 0 to 3. Then from the rest of the process P4, highest priority is P4, so P4 will execute and the burst time is 5, so 5 plus 3 is 8. Then process P1 will execute, so 8 plus 4, 12 at 12 milliseconds, and then process P3. P2 is highest priority, yes, P3, which is the 12 plus 4, 12 plus 6, 18. So now, if you calculate the waiting time, again, waiting time for process P1 is 8, waiting time for process P2 is 0, waiting time for process P3 is 12, and waiting time for process P4 is 3. You can calculate the average waiting time, right? So these are the average waiting time. So here the burst time does not matter, only the priority matters in case of priority algorithms. Then next comes out to be the round robin scheduling. In case of round robin scheduling algorithms, a time quantum, a time slice is assigned basically to the CPU. That CPU can execute each process for that certain time slice. If after this time, if process is not complete, then it will be preempted and next process will be added, right? So it is basically highly fair. There is no starvation because every process will get the time till that time slice for its execution. It is very good for interactive system. The problem is here the size of quantum. If your time slice, if your quantum size is too large, then it will be similar to FCFS. But if your time slice is very small, then there will be number of context switches which will again increase the overhead. There will be high overhead. So we need to choose the size of time quantum, time slice very intelligently so that it is not too big, not too small. How to perform it? Let's see an example. Okay, let's say we are having four processes. Yes, P1, P2, P3 and P4. Just look carefully. The burst time for P1 is 5, the burst time for P2 is 3, the burst time for P3 is 8 and the burst time for P4 is 6. And my time quantum time slice is 4 milliseconds. That means each process will be executed for 4 milliseconds. Now, let's draw the Gantt chart. It is not here. Now, first of all, process P1 will execute. It can execute only for time slice, that is for 4 milliseconds. So it will execute for 4 milliseconds. So P1 has executed for 4 milliseconds. So its 1 millisecond is left. Then process P2 will come in the queue. P2 will execute. Its time is less than the time slice. So it will execute only for 3 milliseconds. So up to 7. Process P2 completes. Now the turn of process P3 comes. again it can execute only for 4 milliseconds. Whether its burst time is 8, but it can execute for 4 milliseconds. So 7 plus 4, 11, and the time left for 4 is P3 is 4. Then the turn of process P4 comes. So it will also execute for 4 milliseconds. So 11 plus 4, 15. And the time left for P4 is 2. Now again after the P4, again we will go to the beginning of the queue. That means the process P1. Its time left was 1 millisecond. So it will execute for 1 millisecond now. So again P1 will execute up to 16. Process P1 also completes. Now we will come to the P3. 4 millisecond burst time was left and my time slice is also 4 millisecond. So 16 plus 4, 20. It will execute for 20 milliseconds. It is terminated. Then P4. 20 plus 2, 22. And P4 also completes. Now, if you calculate the waiting time of each process, let's talk about the waiting time of process P1. Process P1 is executing 2 times here. Okay, process P1 is executing 2 times here, here and here. At this point, it waited for 0 millisecond. It completes at 4 and then it starts at 15. That means in this time, it is waiting for its turn, which is 0 plus 15 minus 4, which comes out to be 11. So the waiting time for process P1 is 11 milliseconds. Now waiting time for process P2. P2 executed only once, and so the waiting time for process P2 is 4. Waiting time for process P3. P3 is again 2 times. One is here, one is here. The first time the process P3 has waited for 7 milliseconds, and the second time it waited for 16 minus 7. 16 minus 7. P3 16 and 16 minus 11, because it completes execution here. 16 minus 11. So it comes out to be 7 plus 4. 7 plus 5, which is 12. Right? Then process P4. P4 executed 2 times here. One is here, one is here. For this point, it has waited for 11 milliseconds. And for this point, it starts at 20, but earlier it has completed at 15. So 20 minus 15. So 11 plus 5, which is 16, which is the waiting time. So waiting time for process P1 is 11, for P2 is 4, for P3 is 12, and for P4 is 16. You can add for 4 of these, divide by 4, you will get the average waiting time. Now, if we talk about the turnaround time, process P1. Okay, let's say here turnaround time for process P1. P1 completes at 16 milliseconds. P1 completes at 16 milliseconds. So the turnaround time for P1 is 16. Process P2 completes at 7. So the turnaround time for 7. Process P3 completes at 20. So the turnaround time is 20. And process P4 completes at 22. So the turnaround time is 22. If you add 4 of these and divide by 4, you will get the average turnaround time, which should come out to be 16.25, and average waiting time should come out to be 10.75. Then shortest remaining time first. It is the primitive version of shortest job first. If a process is executing and the same time a new process with smaller burst time comes in the queue, so the CPU will stop the current process and it will start executing the process with the next smaller burst time. The primitive rule basically compare its burst time to the remaining burst time of the currently running process. If the new burst time is shorter, preempt the current process and start the new one. Otherwise, add the new process to the ready queue ordered by the remaining burst time. The process with the shortest remaining time burst is ready queue is selected first. Now, let's say for example, we're having the four process P1, P2, P3, P4. Now make sure, just check carefully, their arrival times are different. Earlier in the previous examples, we have taken the arrival times same, 0. But now their arrival times are different, right? And these are their burst time, 8, 4, 9, 5 are the burst time. Now, at time 0, process P1 reaches the ready queue. So it will start executing because this is the only process. So it will start executing. So P1 executes and it starts with 0, but after 1 millisecond, process P2 enters the queue. After 1 millisecond, process P2 enters the ready queue and the burst time of P2, which is 4, is smaller than the burst time of 8. So after 1 second, after 1 millisecond, P1 will be permitted and P2 will be loaded. P2 will be executed by the CPU. So it is executed for the 1 millisecond. So the remaining time of P1 is 7 now. Now P2 is executing. After 2 seconds, P3 come, which is having the higher burst time than the P2. After 3 milliseconds, P4 come again, which is having the higher burst time than the P2, which means P2 will execute first now, which is 4 milliseconds, that means 5. Now, all the processes are in the ready queue with their burst time. P2 is complete. Now, out of the remaining processes, which is having the shortest burst time, which is P4. So, P4 will be executed now. So, 5 plus 5, which is 10, because the burst time is of this is 5. Now, it is also complete. Out of P1 and P3, which is having the shortest remaining burst time, is P1, which is 7. So, P1 will be executed again. Then, after that, P3, 17 plus 9. Right? So these are their burst time. Yep, this is their Gantt chart. Okay. Now, if we compute their waiting time, the waiting time for process P1, if you see here again, process P1 is being executed twice. So waiting time is 0 plus 10 minus 1, which comes out to be 9. Waiting time of P2 is 1. Waiting time of P3 is 17 and waiting time for process P4 is 5. We can calculate the average waiting time. If we calculate the turnaround time, for process P1, the turnaround time is 17. For process P2, the turnaround time is 5. For process P3, the turnaround time is 26. And for process P4, the turnaround time is 10. So we can calculate the average turnaround time. Yes, average turnaround waiting time comes out to be here 6.5, 9015.2. 9015.2. Yes. Oh, Yes, the waiting time for P2. Yes, just a mistake. Average waiting time for P2. P2 has reached at 1 millisecond, and as soon as it reached here, it is getting the turn. So its waiting time is minus arrival time, which is 0. Same for the P3, it's 17 minus 2. That is the arrival time because it is reaching at arrival time too. So it comes out to be 15. And for the process P4, if you subtract the arrival time, so it is 2. So the waiting times are 9, 0, 15 and 2. Yeah, we didn't consider the arrival time, but we need to consider the arrival time also. So these are the turnaround times. Yes, same for the turnaround time also. Actually, we need to subtract the arrival time. So if P1 arrival time is 17, P2 arrival time is 4, P2 turnaround time then becomes P3 turnaround times becomes 26 minus 2, so it comes out to be 24, and the P4's turnaround time becomes 10 minus 3, which is 7. So these are the turnaround time. Yes, waiting time and sorry, turnaround times. These are the turnaround time. Finish time minus arrival time. Right? Okay. So now it's your turn to do some of the questions. One question for FCFS and non-primitive SGF. These are the four processes with the given burst time. You need to compare their turnaround time. The solution is on the next slide, but do it yourself. Another one is using for the round robin. The next one is for the SRTF. These are just some of the practice questions you need to do. Again, SRTF is a primitive version of SGF. Our goal is to minimize the average waiting time. It works always by selecting the process with the shortest remaining CPU burst. It is a concept, academic concept basically SRTF, because we do not know the burst time of the next process which is coming in the queue. So it is practically it is impossible basically to get that which process will have the lowest burst time. If we revisit again threads versus processes, process is a heavyweight process, thread is a lightweight process. Key difference, threads, all the threads reside within the same process, so they share the same address space. So threads are much faster than the processes. Why we use threads? Due to the responsiveness, resource sharing, economy, scalability and performance. So we use, these are the some of the reasons why we use the threads. These are some of the differences between the user threads and kernel threads. User threads which are created by the user processes, whereas the kernel threads which are created by the operating system itself. So kernel threads always implemented by the operating system, whereas user threads are created by the user processes. In multi-threading models, um, we can map different user threads and kernel threads. We can have a many-to-one model, one-to-one, many-to-many model. These all are the terms which we have discussed earlier. So yeah, that's all about this unit. If you have any issue, just let me know. Thank you.